I'm now going to talk about fermions, something I've neglected up to now. First, I'm going to explain why it's difficult. The obvious reason is that this phi of t that we wanted to interpret as a probability is obviously not a probability, because for electrons, if you have more than 2 electrons, then when you exchange 2 ones with the same spin, it changes from plus to minus, or from one complex number to another. And there is a way to do this, but it's not totally satisfactory. There are 2 ways to do it. One way has a problem with efficiency. That's the exact method. And the second way introduces an approximation. That's the fixed node method. So I'm going to explain those now. And so actually, this is the answer to your question about what I did over in the blackboard there right before the break. This is the so-called transient estimate approach, which is exact, but it has a problem with efficiency. So basically, if we take our trial wave function and we apply this operator, is exactly what I was doing over here on the board, we get a trial function defined as a function of beta. And we can calculate this thing, which is like a partition function, z of beta. This is like the modulus of the wave function, the normalization of the wave function, given by this. And we can expand it out in this kind of trotter-like path, R0, R1 up to Rp, p points on the path. And this would be like p steps of diffusion Monte Carlo. And then to calculate the energy, we put an h in there. This would be the energy after a time beta. And it's you can commute this h through this projector here, e to the minus beta h, and that would act on the trial wave function. So that would be the local energy of the trial wave function. This is all going to be related to what I'm going to talk about now is, first of all, about the Fermion problem, and then about reptation Monte Carlo, where we use this. So there's several properties. For one thing, this psi of beta converges to the exact ground state. Okay, we haven't yet interpreted this as a probability. We have to do that next, but I want to say, first of all, this is the projector theorem that this wave function at large beta converges to the ground state. And it's an upper bound that converges to the exact answer monotonically. Now, how do we interpret this expression here as a probability? Well, what you do is, first of all, these factors, which is the density matrix, are always positive. All of these factors are positive. The problem is in this trial wave function here, psi of R0 and psi of Rp. So we have a trial wave function at both ends of this random walk, symmetrical in the random walk. Okay, so what we do is we take the modulus for the probability, and then sigma of R is the phase of the wave function. So we split the wave function into modulus and a phase. Now, if you're dealing with a no magnetic fields and non-degenerate ground state, then you can actually make them real wave functions. And so sigma would be either +1 or -1, dependent, and this would be just the modulus. So we can think of sigma as positive or negative. Okay, so we can do the random walk with this part in black, and then just carry this along as an estimator. So if we want to, for example, calculate the normalization of the wave function, that would just be the sign at the beginning of the random walk times the sign at the end of the random walk. And therein lies the problem. here is an example. The trouble is when you talk about mini fermion systems, it's in such a high dimensional space, it's hard to get a physical feeling for what's going on. So here we have related it to a one particle in a box as an example of a fermion problem, just two-dimensional problem. So we assume that the box has a symmetry around this point here. So V of R equals V of minus R. There's a symmetry around here. So this potential is the same as that potential. This potential is the same as that potential. This is a vector here, R. And we don't want to get the ground state. We want to get the first excited state. We want to get the first state that is antisymmetric about that point, right? You know, if you have the symmetry, you can classify the states as symmetric or antisymmetric, right? Parity. So we want to get this one. Now, the problem is that's not enough to decide when the wave function changes sign. This might be the solution, or that might be the solution. You don't know. That depends on the potential, which I haven't told you what the potential is. I've just told you it has this symmetry. So the transient estimate algorithm is we start out walkers according to some trial wave function, and then we evolve them, and maybe this is the exact solution. It evolves from here to here. So we assign a plus sign if it's in the red region, and a minus sign if it's in the blue region, and then they evolve, and this is the exact solution. And so to calculate something like the energy, it would be sum over all the random walks in the diffusion Monte Carlo, and the estimate, you have this weight factor, which is the weight at the beginning of the random walk times the weight at the end of the random walk times its local energy, divided by this normalization factor. So you carry along this weight of the random walk, this product of signs, as a weight factor, and the issue is that both of these go to 0 at long time, because essentially the random walks get all mixed up. So if you're in some particular region, like right here, you know, you get some positive contributions and negative contributions, and generally speaking, they'll cancel out, and there will be a signal. Mathematically, there's no problem. You will get this solution, the correct solution, but the noise will mask it. So I have an illustration. So this is the initial distribution. This is like it taking a line, this red line here, going along that line. It starts out with a distribution like this, but later you get overlapping distributions, and eventually the noise wins out. And you can show that the signal to noise ratio goes like this. That is the signal decreases relative to the noise, and it decreases based on the gap to the boson state. The boson state here would be the state that's symmetric with respect to R, where you have f of R equals f of minus R. So, you know, I suppose these are walls. They would be positive throughout this whole region. And that's how fast the noise grows, basically. Oops. And so it's not really a fermion problem, but really an excited state problem. And now there's a lot of, when you first see this, you would say, well, the problem simply is, well, just cancel the walks off. If you were doing this in 2 dimensions, that would be no issue to cancel the walks off. Okay, that you have a random walker that's starting here and goes over here. You could imagine these are two armies that are fighting each other, and you know, this is the boundary between the armies, and then this army goes up here, and I'm sorry, this army comes here and it captures this territory and kills off the opposing army. You could do that with the walkers. if a positive and negative walker are at the same location, you could cancel them off. And actually, there's a whole development originating in Cambridge by Ali Alavi that's called full CI, where they do this actually in a determinantal basis, and they cancel things off. The trouble is when you go up to many dimensions, it doesn't look like this anymore. That if you have 1,000 walkers and say 500 are positive and 500 are negative, the chances of all the electrons in those configurations being exactly the same is 0. So they'll never cancel off. It's more, I think, more like, well, if you were wandering around Alaska, the chances of you running into another human are basically 0, right? So to cancel off, it's just the phase space is so large that you're not going to be able to cancel things off. The only way this can work, and it works in full CI, is that they restricted the bases to just, like 1 million places that are important. And then you can have 1 million walkers, and then they will cancel off. Here's an example of Quan. There's this so-called student here did in his thesis is a transient estimate calculation of the electron gas. And so this is the energy versus time. And you see, this is the signature, is, things come down and then the error bar grows, right? And so the idea is you're getting a sequence of upper bounds. These are two different states, an excited state and a ground state. That both fermion states, so they both have a sign problem. And, so eventually the error bars grow. So sort of you want to take the value, the minimum value, since this is a sequence of upper bounds, you take the minimum value when you add in the noise. Eventually the noise is going to grow and you're not going to get anything useful out. But, you get, this is the, the variational energy. So you get some improvement over the variational energy. So it's possible to do these things, and certainly, this was 60 electrons, and so this is at, it's possible to do things, but, when you get to more complicated systems, you find your error bars grow really rapidly, and actually you can talk to Norm Tubman, who's a postdoc here, about, he was trying to do this for more general systems and had a lot of difficulty. Now, so I just want to tell you what I think the Fermion problem is. We want to write it in general terms, not referring to particular algorithm. And this is one of the, what I view as one of the key problems in computational physics, unsolved problems. If you given a given system with a given Hamiltonian, and you want to calculate a property, say O, the energy, for example, or the superfluid density or something, and there's n fermions. It's a scaling problem in n. So again, we're interested in large systems because most things in nature have thousands or millions of particles. How much computer time will it take to estimate O to an accuracy epsilon? How does the computer time scale with the number of particles and with epsilon? That's the question of complexity. How does it, if you double the system size, how does the error bar scale? How does the computer time scale? And a solved problem, I would say, would be where the computer time scales with a low power of the number of particles, and if it's a simulation, it always scales like 1 over epsilon squared. That's the problem with Monte Carlo. To get another decimal place, it takes 100 times longer. But we're used to that. Luckily, computers have gotten faster. So, a deterministic method may scale faster in epsilon. However, it scales worse in the number of particles. So a classical system, you have alpha on the order of 1 or 2, okay? And we've seen with variational Monte Carlo, alpha is like 3, okay? But that's still okay. The trouble is that the Fermion problem, everything we know goes exponential in n. And so you want to make a method that goes like this. That would be a solved problem. I would view it as a solved problem. But the important part is that all approximations must be controlled. We have many solutions like DFT that are better than this, right? But the trouble is you don't know how accurate the density functional is. So it does not solve the Fermion problem, in my view, until you can control all the approximations. The interesting thing is that there are solved quantum problems, just not the Fermion problem. Any one-dimensional problem, we know, as I'll show you, how to solve it. Not any one-dimensional problem, many one-dimensional problems. One-dimensional, you should not think about solving the Fermion problem and think in one dimension, because it's very, very much easier in one dimension. Particles, electrons on a line are very much easier. Why? It's because to exchange, they have to be at the same place. You know that they have to be ordered on the line, and that makes them much easier. Bosons and Boltzmann-ons that Burckhardt talked about at any temperature, including zero temperature, are solved. So that's frustrating. We can do superfluid helium, and by this criteria, it's a solved problem. But it's superfluid helium-4. But then superfluid helium-3 we cannot do because it's a fermion, right? There are some lattice models that are solved. A famous case is the half-filled Hubbard model that you can show, that you don't have a sign problem on there. Other problems, fermions in special boxes, certain lattice models. Anyway, those are what I would view as solved problems. But it's not the problem that we're interested in. Is you take in, say, hydrogen atoms in a box. Is that solvable or not? Because there are protons and electrons there that are fermions. So is that a solved problem? We don't know. So we don't know how to solve that problem. We also don't know where the dividing line is between solvable problems and unsolvable problems. You often see quoted in the literature this statement from Wiesa and Troyer that the Fermion problem is NP complete, but that's actually something we disagree with. What they showed is that there exists at least one quantum problem that's really difficult to solve, but it's not necessarily the problem that we're interested in. There exists a quantum lattice model which is really difficult to solve, but we don't know whether something like the Hubbard model is also difficult to solve. So it's open. That's why I think it's really important. And so I said all this already. It's intellectually and technologically very important. Progress is possible, but it's a more subtle problem. You shouldn't, well, maybe there will be some really bright student that'll solve it overnight, but nobody has so far. And I didn't say it has to be a quantum Monte Carlo approach. You can try other approaches. There's something called diagrammatic Monte Carlo, for example, or some other approach to do it, perturbation theory or whatever. But you have to be able to control all of the errors. This is only one of a group of related problems. What I mentioned earlier is that the dynamics problem, that is real-time dynamics, in my view, is a much more difficult problem than the sign problem in equilibrium statistical mechanics. Feynman argues that general many-body quantum simulations is exponentially slow on a classical computer. And he makes an argument which is correct insofar as it goes. That is, if you wanted to write down the many-body wave function, it would take an infinite amount of time. But that's not the question that we actually have. We don't want to calculate any possible property of the quantum system. It's easy to see that that would be too difficult. But what about calculating the energy of a quantum system? We don't know if that's possible or not in a finite amount of time, basically. So it's a question of what property. You can't say any property of a quantum system, but things that we're interested in that you could conceivably measure in the laboratory or that have some relevance to measurable properties. That's what you want to calculate. And of course, there's a whole large field of physics trying to make either quantum computers, either the digital kind or the analog kind. Actually, we're part of a project to make a quantum emulator out of cold atoms in lasers, atom traps, and try to make like a two-dimensional Hubbard model, so that you could actually. This is like doing an experiment of the Hubbard model. A Hubbard model is a lattice, a square lattice, and spin 1/2 particles on there. And you want to make cold atoms look just like a Hubbard model, and then do an experiment on them. That would be great. But after 5 years, it's proving more difficult than we thought 5 years ago to do this. And so that would be another approach. But when I say the Fermion problem is could you do it on a classical computer? That is the kind that we're used to, this kind, or not a quantum device. Anyway, so that's the Fermion problem. And you had a question back there, or just scratching? Anybody have a question about this? So this is a key problem. And again, the problem is not to make an approximation that's really good for your system. The problem is to show that there are no uncontrolled approximations, right? That's a different issue. I mean, for example, density functional theory, they have really good functionals. It's really great. You can solve a lot of problems, but you still don't know if they're controlled, those approximations. That is, can you show mathematically what the error is in advance of an experiment or whatever? So anyway, any questions? Okay. So now we're going to talk about the fixed node method, which I mentioned. The transient estimate method is exact. However, the error bar decreases very slowly the bigger the system gets. The error bar decreases slower and slower. And that was what I was showing here. See, the error bar decreases, and it has a factor of n in there. So if you double the size of the system, the error bar decreases slower and slower, right? So it's good for small systems and good for bosonic-like systems, but it doesn't really converge like this. So the fixed node method actually is not a solution of the sign problem. It just says, let's get rid of that sign, but then you make an approximation. And basically the idea is you set remember this F is the mixed distribution, and you set the trial wave function to, the exact wave function or the solution to 0 when the trial function vanishes. We're working with real wave functions now. And you can show that if you do this, this is a constraint on the solution. It's like in the box that I was showing you. We're saying, okay, this is my trial node here. It may not be perfect, but I'm going to just solve the Schrodinger equation in this region and solve it in that region, and I'm just going to put a boundary condition that it vanished there. Unfortunately, it's an approximation because maybe this is actually the boundary condition we should have used and not that. But we're going to take the best trial function we have and assume that the nodes are also good. But we do better than variational Monte Carlo because we exactly solve the wave function in this region, right? So we get all the correlation, all the many-body effects in this region. It's just that the shape of the division between the red and the blue is not quite correct. Why is it not quite correct? Well, when you put a zero boundary condition on here, the gradient of the solution may not match across this line here. So you may get a mismatch of gradients. And that means in terms of our diffusion process, once you put a barrier, this is like the Berlin Wall here, the economies of East and West Berlin are no longer in equilibrium, right? So you have a wall here and you don't have exchange across there. So you have like a discontinuity in derivatives at that point. And you could get a lower energy solution if you allowed the wall to adjust, all right? So this is be a lower energy solution. But inside these two regions, then you have the exact solution. It's just you have a mismatch, an error at the boundary. And so you get the best upper bound, you get an upper bound to the energy, you get the best upper bound consistent with the boundary conditions, and you get the exact solution if you happen to have that wall in the right location. I said all this. You have, it scales like variational Monte Carlo. Essentially you're doing, you have to calculate the trial function. All the scaling has to do with calculating the trial function. And we'll show the generalization to finite temperature. Burkhardt already talked about that, magnetic fields and continuum and so forth. This is the proof of the fixed node upper bound theorem, but maybe you can just read this on the notes since I'm so far behind here. But basically, you can show that the constraint just raises the energy. Now, if you would have solved the sign problem if you knew where to put the node, and this is where one dimensions are special. If we know the sign of the exact wave function, we just have to know what the sign is. We can solve the Fermion problem. The nodes are where the wave function vanishes. This is a mistake. Sorry, that should be phi. When I converted from a PC to a Mac, all the fonts got messed up, but okay. The nodes are a 3 n minus 1 dimensional surface. The coincident points are when two electrons are at the same place, two fermions are at the same place. Those are three equations, so that's a 3 n minus 3 dimensional hyperplane. Now, if you were working on a line, one dimension, this dimensionality is the same as that dimensionality, and that's what I said already. Fermions in 1D are easy. You just order them on a line, and that gives you the exact solution. Usually. Sometimes you can have extra nodes. So here's actually a picture I think Burkhardt already showed you. Here we take 161 fermions in a typical location in two-dimensional box, and then I just drew where the nodes were, and you see how complicated it is. These are not the nodes you're thinking about in the wave function, like come out of DFT calculation. Those are three-dimensional nodes. These are 3n dimensional nodes. And so if you take the many-body wave function, you locate, you have this huge space, and we take a two-dimensional slice through the space. This is what the nodes will look like. And you see where the other electrons are, the nodes connect where they are, and so the node has to go through all the dots. It's like one of those children's drawings where you connect the dots. But in the children's drawing, they tell you how to connect them, right? But here, nobody tells you how to connect them. And that depends on the potential, right? And so you can see, actually, this last electron is moving around. And this shows you how it changes sign. And there's a node, essentially, every interparticle spacing, and actually the momentum distribution, the fact that there's a discontinuity says that there has to be a structure in these nodal surfaces. The nodes divide space into exactly two regions. I mean, you may think that there are lots of different nodal regions here, but that's only because we're looking at a two-dimensional cross-section of a higher space. I conjectured, and Lubos-Mitas proved, that you can get from any point in this space to any other point in the positive region by avoiding the nodes. So the nodes are like my two hands. They're just two hands, and they cover the whole 3n-dimensional space, but they're very much interleaved with each other, right, the two regions. So that means that when you're doing diffusion or fixed node Monte Carlo, if you start in one place in the many-dimensional space, you can go everywhere without crossing a node, usually.
So you're saying there's no islands,
Right.
right?
And I should say, there are conditions on this theorem. There are conditions that say that, for example, you have to have a local Hamiltonian. You have to have, it's not true of any antisymmetric function, but it's true of ground states, right? And the way you prove this, essentially, is by saying that if you had an island, you could lower the energy, so it couldn't be a ground state. You could, by getting rid of the island, you could lower the energy. Okay, here is, if you have, I've talked about wave functions being real. What if you have a complex wave function? Well, this can happen. Well, it can happen if you have a magnetic field, but it can also happen if you apply what are called twisted boundary conditions, which we might get to a little later on. If you want to deal with non-zero momentum states, or say certain, if you write down the ground state of an atom, say it's in a p state, you know, you have m equals 1. If you want to put it in a m equals 1 state, then it has a complex wave function, right? Well, there is a generalization of the fixed node method to the complex wave function. It's called fixed phase. It's actually, in a way, more fundamental. Basically, you can show that you can get this a nodeless, a diffusion Monte Carlo solution for a complex wave function. Conceptually, very simply, you write down a wave function. The log of the wave function is u of r, right? And this can be a complex number, u of r, complex function, okay? And now let's write down the variational energy of this wave function. And if the Hamiltonian is Hermitian, the variational energy has to be real, so we can just take the real part. And now we're writing this down. This is psi squared, and when you take psi squared, you're just taking the real part of u, and I have it in the numerator and denominator. This is the variational theorem. And now this is the local energy of this wave function here. I mean, essentially, and basically we have the potential energy, and we have del squared of u, and now we have something which is the gradient of u squared. And we have two terms. We have the gradient, now I'm writing in terms of the real part and the imaginary part. Here, we have the gradient of the real part squared, and we have the gradient of the imaginary part squared. And we do not have the cross term between the real and the imaginary part, because that would be imaginary. And we know that the variational energy is real. So we can drop that term. Okay. Now, let's suppose that we do what we call fixed phase. That is this wave function. We allow the imaginary part to be fixed, so we know what this term is. And now we allow the real part of u, which is here and here and here, to be determined by diffusion Monte Carlo. So we just have an effective potential, which would be this. We have to include this part and that part. And I threw in a magnetic field, but it wasn't there before, but I just threw it in here. But basically, if we don't have a magnetic field, you can just drop this vector potential. And so if we work in our diffusion Monte Carlo with this as a potential, V of r, and then gradient of the imaginary, the phase of a trial wave function squared, then this proves that we get the best upper bound consistent with this phase. So now if we say, okay, we're going to deal with a real wave function, then u would be the phase. This is the phase of the wave function, would be plus or minus 1, and this would give us a delta function when the modulus goes to 0, and then we would essentially reduce down to the fixed node method. I guess I didn't say that here, but this reduces down to the fixed node method if it turns out that this function here is real. So this generalizes things to to complex wave functions, and this is what we use when we use twisted boundary conditions. We essentially put in an effective potential given by the gradient of the phase squared. And we can do things like vortices or phonons or various excited states that are naturally complex with this formalism. Okay, this is the next topic, very briefly, about improved wave functions. Are there any questions about diffusion Monte Carlo? So I talked about, we had a lot of discussion before the break, and now we introduced fixed node, which says how we treat Fermi statistics and also how we deal with complex wave functions. Yes? Nick?
So do we need to sample like just positive pockets, negative pockets, or both, or?
Oh, in the question in diffusion Monte Carlo, you have to sample positive pockets and negative pockets separately? Is that your question?
Yes, or does it have?
Okay. The answer is this is the theorem, which I call the Tiling Theorem. Is the following theorem, which I kind of alluded to earlier. But the Tiling Theorem is if you take as your trial wave function the solution to a physical problem. It doesn't have to be the problem you're interested in, but any solution to a physical problem, like a DFT problem, or a free particle nodes or density functional nodes, they have a tiling property, and that is if you start with one point in the phase space and go to all the points that you can reach without crossing a node, we call that a tile. Now, if you relabel the particles in that tile, as you start at a point and you ask all the other points you can reach, that's the tile. But suppose you started at that point and then you relabeled the particles with an arbitrary permutation. That can either map it into the same tile or it can map it into a different tile, right? So in principle, you could have n factorial tiles. The theorem is if it's a ground state, that all those tiles make up the whole space. There's nothing else. There's not another, it's not like a tiling pattern where you have two types of tiles. So you would have to sample both A tiles and B tiles. There's only, this design is made out of all one type of tile. They may fit together like this. Well, my hands are different, but in many-body configuration space, all the tiles are the same. So that means it doesn't matter where you start from. That's the answer. That's true for the ground state. You can prove that that's true for any ground state, but any ground state of a given symmetry. So it would be true of, for example, the like the P state of a hydrogen atom, or the D state, or the F state, or whatever. But it's not the 2P state, or the 3D state, or the 4F state. It's not true for the 3P state, because that's not a ground state of that symmetry. And so, in fact, let's talk about, you have the 1s state, of course, is bosonic light of a hydrogen atom. The 2s state then has a node, you know, so this is the ground state, the 1s state. The 2s state looks like that, right? So this has two different regions. This region and that region. And they are not related by symmetry. If you're going to do diffusion Monte Carlo of the 2s state, you would indeed have to do random walks there and there, and you would, unless you had the node correct, you would get different answers. And you would not have an upper bound property also, but we might get to that eventually today. But for a ground state of a given symmetry, then it doesn't matter where you start from. assuming your Slater determinant that determines the nodes is the ground state. If it's a bad solution, like it's a DFT calculation that's not converged very well, then you could maybe violate this. Yeah?
Could you dynamically improve the nodes somehow?
Yes. The question is, could you dynamically improve the nodes? Yes, you could, but the only way I know how to do it is within a parameter space. Suppose you have a trial wave function that has some parameters in it that affect the nodes. For example, suppose take our nodes from a DFT functional like the Beckey potential that has a parameter, right?
And
you could say that parameter was a dynamical variable, and you could then have the diffusion process go to the best value of that parameter. But you're still in that, you don't know if that's the exact solution, it's just the exact solution within that subspace. Yes? Mm-hmm. Any other questions?
So if I understand, just follow up on his question, if you have a bad guess wave function, but the nodes are exact,
yes,
then DMC will give you the exact.
That's right. He asked if you have a bad wave function, but the nodes, like in one dimension, happen to be exact by symmetry, you will get the exact answer. That's right.
Couldn't you do some kind of, I don't know, diffusion or whatever moves?
Can you make some sort of move that, well, nobody that would actually solve the Fermion problem. That's the problem. Nobody knows how to do that. Without, it's not just a matter of on paper working, but in practice in this many-dimensional space being stable, right? Being not susceptible to noise. It's a problem of, well, that's the subject for more discussion, maybe on Friday if you want. Okay, any more questions? Okay, improved wave functions. Just want to mention this will be fairly short. I'm not going to go through all improved wave functions. I know that this is kind of just give you a taste of improved wave functions. Why am I talking about this now? Well, obviously, if you can improve the wave function, then you can get better nodes, and then you can get lower energy, and you can get closer to the exact solution. So we're going back to the variational method in a way. And Burkhardt mentioned the Feynman-Katz formula, which is, I think, conceptually a very nice way of thinking about improved wave functions. And this is actually what I called forward walking a minute ago before the break. If, in terms of diffusion Monte Carlo, the exact wave function at large time, this is the exact wave function, relative to the trial wave function. This is the population coming from a point R0 after a time t. Asymptotically at large time equals the exact wave function over the trial wave function times a constant. Okay, and just imagine doing this analytically. We can write this down as the exact wave function is equal to the trial wave function times the integral of the local energy of walks starting from R0. So I imagine, just like when I was doing that nuclear fusion problem, we start at a point R0, we send out an infinite number of random walks from that point with our guiding function, psi trial, and then we integrate the local energy along each of these trajectories. That's what this is, right? And then this brackets means you average over many of those random walks that are guided with the trial wave function. This gives you the improvement to the trial wave function, okay? Now, at this point I introduce an approximation. I take this brackets and I move it up to the exponent. And this is, of course, good if the exponent is small. This is an exact formula, but this is an approximate formula. But I'm going to do this not with Monte Carlo, but with analytically. So again, this is the procedure we use to go beyond the Jastrow wave function. This is kind of a smoothing operator. So we take an initial trial wave function and we generate, say, the nth generation, and we generate a better trial wave function by multiplying by this factor. What is this factor? Is the local energy averaged over some sort of local region. Okay. Now, suppose we start initially with just, suppose we're doing the electron gas, and we have a bunch of electrons in a box, periodic box. The simplest wave function is just a Hartree-Fock wave function. So just plane waves. This is the simplest wave function. It's actually what we call a Hartree wave function, where we don't have any antisymmetry. What would the local energy be of this wave function? Well, the local energy, this is an exact solution for ideal particles. So it's an exact eigenvalue of del squared. So the local energy would just be the potential energy for this wave function. Okay? So what would this be here? It would say you want to take the potential energy and smooth it out. And so the potential energy for the electron gas is 1 over R potential. You smooth it out, you get the Jastrow factor. So that's where Jastrow wave functions come from. They're just a smooth version of the potential energy. So that's phi 1. Phi 0 is free particles, phi 1 is Slater-Jastrow. You still have this piece in there, and but then you multiply by U. U is just a smooth version of V, and you could think of that, now you optimize it. You try to get the best possible U. You try to optimize this Jastrow wave function. Now, of course, I introduced all this to do it one more time. What is the local energy of this wave function? Well, the local energy has this form. There's 2 new terms. This is just a potential-like term, which we already have. But we have these 2 new terms. This is called the 3-body term, and this is called the backflow term. And so this term, you see, has an I in there. So it's like, it's something that modifies the initial value. And this term is like a bosonic term. If you had just fermions, you wouldn't have this term or that term. You just have this. So this is a bosonic term, and this is what we call 3-body because W is like a potential. So this is like a force squared. And so this means that if you're at a given point in phase space, you calculate the electric force on a given electron, and it's proportional to the square of that force. That's the kind of term that you want to add in. So you add in a term like this, and you have some new variational function, zeta here, and this is what zeta looks like for electron gas. I mean, it's some function that you can add an additional parameter. And then you have, and then the backflow is this other term. And if you put it in, remember a Slater determinant, we had, this was our Slater determinant of plane waves. So we're going to change R to X. This doesn't mean the X coordinate, this just means another vector. Okay, X is defined as the electron coordinate plus the backflow. Basically, I think about it as sort of dressing the electrons, that an electron gets pushed to a new position, depending on, this is like a force from the other electrons. So if a given electron is in a symmetrical environment with other electrons sort of equally arranged around it, nothing happens to it. But if it's in an arrangement where there's more electrons, say, to the left and the right, it pushes the electron coordinate a distance away. And here's actually work of Kwan that's here. on the electron gas. This is this eta function that you can regard as a variational function, for various values of RS. And I don't know if this is the best graph I have. Let's see if I have another one. Well, I guess I'll use this one. This shows you how the energy and the variance of in variational Monte Carlo of the wave function improves as you add these terms. Okay, if you were doing Hartree-Fock, you would be up on the 3rd floor. The energy would be really high. This is the variance. That is this is the fluctuation in the local energy. So I'm plotting the average value of the local energy on this axis and the fluctuations on the local energy on this axis. So Hartree-Fock would be up there somewhere. And then when we do Slater-Jastrow, we get this point, the best Slater-Jastrow wave function. And then we add in the 3-body, the bosonic term. It comes down here. And then we add in backflow. It comes down here. And this is where we think the exact answer is, down here. Of course, the exact answer has 0 variance by definition. And we don't know really what the energy is, but by various estimates, it's somewhere around in here, transient estimate or other calculations. So you see that very interesting thing that they sort of fall on a line, and they sort of, this backflow term captures sort of 2/3 of the missing energy that Slater-Jastrow missed. And this other graph on the previous thing showed as a function of density, but that's probably not so interesting. Now, what I put on here is actually fixed node diffusion Monte Carlo. So you can take the Slater-Jastrow wave function, and then you can just do fixed node on that, and you see automatically you end up here. I didn't plot the variance because I don't know, it's hard to calculate in diffusion Monte Carlo what the proper variance, but anyway, the energy decreases down to here. That's what I mean by diffusion Monte Carlo is sort of an analytic way, an algorithmic way of improving your wave function. Without doing any more thinking about wave functions or programming, calculating wave functions, just by adding this branching process to your code, you immediately get all the effects of backflow, right? However, if in addition you go to that extra effort and put backflow in your wave function, variationally you would come down here, but fixed node you would come down here, very close to the exact answer. So obviously the thing is to do both diffusion and Monte Carlo and better wave functions. Now this backflow trick works really well for homogeneous systems like electron gas. Let's see. Here is atoms. I have this graph. I guess you guys can see that. Probably not in the back, but I'm sorry. Again, my graphics is not very dark, but this is atomic number Z here. So 10 is neon, I remember, so forth. Yeah?
Using this generalized Feynman-Katz thing, what's the next order after backflow then?
The question is, can we use Feynman-Katz and go beyond backflow? You can write it down and you get these complicated tensor products. I've always wanted to have a student that knew Mathematica that could just take it and come out with a code. To date, the problem has been to do these things efficiently. Like backflow, it took us like years to figure out how to make efficient codes. And of course, computers get faster. It's less important to be efficient, but okay, you can sort of see what's going to happen. You get here, the wave function was just like a potential. And here you have a gradient squared, and here you have a gradient times k. Okay, so next order, you're just going to get more gradients and more, you're going to get like a gradient of y, gradient of z times k, and different combinations of gradients and different tensor products. With by symmetry, that's all you can have. Now there's an interesting question which maybe you can lead up to. does this lead to the exact solution at some point? And the answer is probably not for all systems, but I don't know if it's really been proved or not. But what you're doing is expanding the wave function, which is a three-dimensional object, in terms of one-dimensional functions. Like the Jastrow function is a one-dimensional function, essentially, and these W and Y functions are one-dimensional functions, too. And so you're sort of, it's kind of a huge reduction of information that is a three-dimensional function is getting mapped into these much simpler functions, but actually it probably doesn't lead to the exact answer, and I don't know the answer anyway. So, but anyway, back to this graph. This shows you the amount of correlation energy that you get with the best single determinant for these atoms. The atoms from hydrogen up to whatever that is. I don't know, what is 17? What? Anyway, I don't, neon, and you know, you have sodium and so forth, aluminum. There's two curves here, which I'll trace out. This is variational Monte Carlo. So you get sort of 80% of the energy. And there's a big dip here, and this is chemistry, right? Carbon and oxygen, things like that, are not very well described by a single determinant. So obviously you need to go to a multi-configuration wave function in order to describe these atoms. Even if you do fixed node Monte Carlo, then you get more of the energy. You get 90%. But that's still not that great. I mean, it's much better than Hartree-Fock. By definition, Hartree-Fock is 0. So Hartree-Fock is down here, right? So you get, you know, we do say you get 80 or 90%. You get 90% fixed node. And I think the thing that was confusing in the first few years when we were doing, this is 2, 3, 4, let's see, this is 2 here. So this is helium. Of course, you get all the energy by definition on helium. And you also do incredibly well on lithium. And then it starts dropping off. And then you go back up, and neon, you do pretty well, and so forth. So, so this was the state a few years ago. Recently, I don't know, maybe Jeremy or Eric Disterly will talk about this. There have been algorithms invented to do multiple determinants in variational Monte Carlo, and being able to do like hundreds of determinants is much less expensive than we thought. So, of course, you can do a whole lot better. You can do essentially exact results if you include several determinants, and not just a single determinant. The other thing that I was talking to you about was the doing geminal wave functions. And that's another thing that improves the quality a lot, but I don't have a view graph on that. We can discuss that later on if you like. That is including two-body effects in the determinant.
About the multiple determinants, the coefficients in front of the determinant, they are variational parameters in the
Yes, they could be variation. They're actually easy to get. The coefficients in terms of the expansion are relatively easy to determine in variational Monte Carlo. That's what we'll hear about tomorrow, actually. So this is kind of my summary about the t=0 method that I talked about before. This is a complicated diagram. This is the error, and includes both statistical and systematic effects, the sum of the two. It's on a logarithmic scale. Originally, I did this for many-body hydrogen. Here is computer time, the log of computer time. So when you see a number like 10 to the 6, well, that's kind of our computer budget for the year, right? Over here. Okay, so if you take a very simple trial function, say a simple Slater determinant, if you do variational Monte Carlo, you always come down a slope of a half here. Then you hit the error of the Slater-Jastrow wave function, and essentially, what's the point of running longer? Your systematic error doesn't improve. You switch on diffusion Monte Carlo, and diffusion Monte Carlo is slow because the time step is smaller. So it lies above the variational Monte Carlo in terms of computer time. It takes longer, but your systematic error is a lot less, so you keep running longer, right? You get down to this point. This point, it plateaus off too. But you can do these release node, but unfortunately they converge even slower, right? The slope is less than a half. And so, they do mathematically converge with transient estimate or release node, but at a slower rate. And that depends on the number of particles. Now, the better strategy is to go to backflow, and then you go from these two curves down to these two curves. And again, they are better in two ways. First of all, the fluctuations are less in a better wave function. So you gain, even though backflow is slower to compute, the fluctuations in the local energy are a lot less. So you gain in the error bar for a given amount of computer time. But the other way you gain is that this systematic error, or the error of the trough function, is less too. So when you plateau out, you plateau at a different value. But of course, you had to use more computer time to get down to that value there, right? And then you can use fixed node with that too, and you end up with a much better value. Of course, what I was doing is trying to get down into the applications where you, with a reasonable amount of computer time, you can get a reasonable error, right? But of course now, computers are faster, so this little box has moved out, so maybe we're in there. So anyway, that's kind of a summary of my method. Problems with projector methods? Well, it's really a super variational method, so everything I said about variational applies. The diffusion Monte Carlo dynamics is determined by the Hamiltonian. We can get very accurate calculation if the trough function is good, but we need a trough function for accuracy. They're essentially methods that perturb from the trough function to the exact function. So you don't really escape from the trough wave function. So if you put in a trough wave function of Fermi liquid, you kind of end up with a Fermi liquid. If you put in like a certain kind of a state, insulator state, you end up with an insulator. Really, it doesn't really escape. Although mathematically it could, but the influence of the trough function is such usually that it's hard to escape from your initial order that you're putting into the trough function. However, it's much less sensitive than variational. That is, you've gotten rid of a lot of the errors so that, maybe you can do studies of phase transitions better. You have, and then I mentioned all this thing about mixed estimators. It's difficulty calculating properties other than the energy, so you have to do these techniques I discussed, extrapolated estimators or forward walking. Okay. Now I'm going to switch over to finite size effects. And I put in these things, these blank slides, so sort of, to find them on the website, the different talks. I mentioned this very briefly, and so I'll just go through this really quickly. This is an important part of what you do in the lab. It's kind of one of the main problems with Monte Carlo or finite size effects. We're trying to calculate properties of the electron gas or solid hydrogen or materials, and that Ron is going to talk about. And going to the thermodynamic limit is, in a way, is as important as the fixed node error in practice. We do systems of 100 to 1,000 electrons, and this is just, you want to make sure that they're as close to the thermodynamic limit of an infinite system as you can be. Okay, so as I mentioned, we almost always use periodic boundary conditions, and what this means is, that when an electron goes out of one side of the box, it comes back in the other side. That would be all you would need to say for classical mechanics. But there's two issues. One is caused by the kinetic energy, and one is caused by the potential energy. Okay, first of all, I'll first mention the potential energy, and the problem is the Coulomb interaction, the 1/r potential. when you when you have two particles interacting in the box, there's different distances that you could compute. You could compute this distance, or you could compute the distance the other way around the box. Now, the way I like to do it is what's called the image potential. That is, you don't just take the shortest distance, you do both. And in fact, I guess I missed something here, but suppose you have a potential V of R, and you're trying to calculate the potential between, what I missed here is the index of the summation. Somehow I got cut off, but we want to sum over pairs of particles I and J, but also want to sum over the displacements of the box. So in a way, we're embedding this box, we're considering all the images of the box out to infinity. We add all those in. So this becomes a periodic function, and which is differentiable and all these things. And it has a nice property that it satisfies the electrostatic sum rules, which is very important in condensed matter, the fact that you get the electrostatics correct. You're embedding this small system with images of itself, and so all things like Gauss's law that you learn in electrostatics can still apply. If you take this potential and you do just the minimum image, you actually break electrostatics. I won't go through that. I know there are many different ways of doing periodic boundaries. I just wanted to kind of introduce some of the issues. Now, why is this so important? Well, if you take a 1 over r interaction, it's called a long-range interaction. You might think that 1 over r decreases to 0, so let's just make the box bigger and bigger. Well, actually, that's not correct. The reason is that the potential decreases like 1 over r, but suppose you're sitting at a charge at the origin, and you're looking at charges further and further away. The effect gets smaller and smaller. But how many charges are there at distance r away? Well, the size, the area of a sphere is 4 pi r squared. So the effect of charges at distance r away is 4 pi r squared divided by r. So that grows with r. The further you're away, the more important the potential is, naively. Now, how can this work? Well, it works because systems are neutral. So actually, at distance r away, they're both positive and negative charges, and they cancel out, right? So you actually have to include those charges. The trouble with just truncating the potential is there may be a positive charge inside the truncation radius and a negative charge outside. Unfortunately, you draw your sphere right in between, and so you don't have a neutral system anymore. You have trouble because of that. So that's why we use this image potential, which is the Ewald potential, because that's really periodic and you don't have problems like that. So you have two problems, namely you want to make it continuous and have the electrostatics, and you also have to have convergence. And that's what Mr. Ewald did a century ago or so. Also, the trial wave function is long-range in the same sense. I said that this is the long-range potential, but actually the Jastrow wave function decays just as slowly. So you have to calculate the potential energy with these sums, and you have to calculate the trial wave function with those sums also. Now, here is a brief introduction to this method. Okay, here actually I have the subscripts correctly here. So this is the potential, this is the Coulomb potential, not the wave function, or it could be the wave function also, but this is what we want to calculate, and the procedure is that you divide it into K space and R space, and you do the short range part in R space and the long range part in K space, the Fourier transform space. And so this is the Fourier transform of the potential, and so if you take a 1 over R potential, the Fourier transform goes like 1 over K squared. And so this diverges at k equals 0, and this diverges at r equals 0, but those are complementary. So if you do half of the summation in k space and half in r space, it actually converges. And so basically, I hope that you've heard some of this already. We change the real space potential to this arrow function potential, and the k space then is given by what's left over. And you see that both of these are plots of these functions in r space and k space, and both of them converge with respect to their argument. So you have exponentially convergent sums in both r space and k space, but you have both of them. So this adds to the extra work, but actually it's something just like 20% more work than a short-range potential if it's well programmed. Maybe I'll skip over that. In case you're interested, this says how you do the evolved sums on the computer, and this is presumably how QMCPAC does it somehow. And it doesn't converge like 1 over n, it's n to the 3/2 is how it converges. So it's actually worse than, say, a short-range potential, but it's not the slowest converging part. And there are problems with image potential, and this gives you an example, but I think maybe I'll try not to, I'll not discuss that. There's certain correlations that occur in periodic systems that would not occur in nature. But if you get rid of the image potential, you're going to introduce other problems. I'm just warning you of that. So it may be better. What I think is that you have to have a continuum model of long-range potentials to understand the results of a finite system. And that's actually what I'm going to talk about here, is a model. Okay, now back to the finite size effects. That was just a digression about how we treat the potential. That gets rid of the large finite size effects in the potential. But there's actually a larger finite size effect that's caused by the kinetic energy. And this is the momentum distribution of the electron gas. This is actually a really nice calculation a collaborator of mine did of the momentum distribution. I won't have a chance to explain everything. But if you take an electron gas and you take a certain number of particles in a periodic box, suppose we're at what we call the gamma, suppose we're working with real wave functions, what kinds of plane wave, what kinds of Slater determinant do you get? Well, you have plane waves. In the plane waves, if you have periodic boundary conditions, are e to the I k dot r. I think I have that here. This is the kind of wave function periodic boundary condition you have. If it's periodic, then when you change r to r plus L, this has to return to its same value. So that means that k is given by these discrete values. It's on a grid. And this is what I'm trying to illustrate here. The interstitials of this grid are where you put the electron states are given by these grid locations. Now, what would the energy of this system be for a finite number of particles? Well, this is as if you were trying to estimate the energy of the area of this circle by the number of grid points inside the circle. That's essentially what you're doing if you did a Hartree-Fock calculation with periodic boundary conditions. You wanted to calculate the area of the circle by counting the number of grid points inside the circle. Now, if you increase the size of the system, that's effectively making L bigger, and so you get a finer mesh, and you get a better estimate of the area. This was actually, problem was posed by Gauss back 200 years ago or more, of how does this estimate of the area, it was a problem in number theory, converge to the area, or the area is pi r squared, right? How quickly does it converge? And here is the numerical answer. It goes like this. This is the number of particles. This is the number of grid locations. And this is how it converges. This is the error over here, the log of the error versus the log of the number of particles. And you see how slowly it converges to the exact answer. So we're not approximating this sphere very well. Now, what we started doing about 10 years ago is what's been done in solid-state physics forever, is we integrate over the Brouillon zone. And what this means is we don't use periodic boundary conditions anymore. We add a phase, and that's this theta factor. And this is called twisted boundary condition. So now when an electron goes out of one side of the box, it comes back the same value of the wave function, but it picks up a phase, theta. And when we calculate properties, we integrate over this theta, right? And that converts this curve to this curve, which is about 2 orders of magnitude smaller error by integrate. But this introduces complex wave functions, which is why when I talked about complex wave functions a few minutes ago. Here shows, so this is the first thing that you have to do finite size effects is what I call twisted boundary conditions. This is basically more important for metals than for insulators, because see the problem was that the momentum distribution had this discontinuity. So it really mattered whether you were representing the states on this side of the momentum distribution and this side. And the kinetic energy is the integral of the momentum distribution. So it helps to have this axis be continuous to represent all of these states here. And if you use periodic boundary conditions, you only represent some of the states inside the Fermi surface. Now, the other effect, which you can maybe see in the inset, is not the twisted boundary condition effect, but the effect of the potential. And if you just use the, calculate the momentum distribution the old way, where you ignore finite size effects, you get a line like this for the momentum distribution, the solid line. And you might be able to see a light red line here, and that's after you apply a theory of finite size effects, and you see a big change in the momentum distribution, which is all finite size effects. So even after you've done twisted boundary conditions and evolved potential, there can be large effects in the properties of the system. And more details, you could see this paper, but I'm just going to mention how you calculate the potential energy. Whoops. I'm skipping over that part. Okay, the potential energy you can write as the integral in k-space of the Fourier transform of the potential in k-space times what's called the structure factor. The structure factor is essentially the Fourier transform of the electron density. So this is writing the potential energy in k-space in terms of the Fourier transform of the pair correlation function, essentially. Now, there's two approximations when you're working in periodic boundary condition. And the main effect is when you do periodic boundary conditions, you're approximating this integral here with the sum. The sum, again, you have a grid in k-space when you're working with periodic boundary conditions. And the big effect is that the k equals 0 term is effectively missing from the sum. And you essentially can put that back in. Again, this is an analytical model that helps. And you put it back in and you get much better results for the finite size effect. So basically, understanding what the finite size effects are in a metallic system enables you to correct for that, rather than trying to do larger and larger systems. And I think I have a graph here that shows this is the effect of periodic boundary conditions, and then when you correct for that, you actually get, this is a twisted boundary conditions, but actually analytically we know what this curve is here, and we can actually add in a correction and get something essentially flat. So that's you know, it's a whole theory of finite size effects. This is one way of doing finite size effects. In the literature, you'll find other ways. What we did back in 1980 was essentially doing certain sequences of sizes of systems and then using those to extrapolate, doing an extrapolation-based approach. That is, we did like 54, 128, 256, and then we would extrapolate to infinity. The problem with that approach is that now we want to do complex materials that might have a unit cell that has like 512 electrons. The next available system that we could do might have 5,000 electrons, and we just can't afford it. So now we have methods that enable us to do finite size corrections with a single size system using a theory based on the correlation functions that you can calculate. In this case, the momentum distribution and the structure factor that determine the energy. And we say how those are affected by the periodic boundary conditions. Okay. You guys must be getting hungry and tired. Okay, it'll finish. I'm going to miss the reptation. Maybe we can fit that in. But somebody asked me about how you calculate a ferromagnetic transition. I'll just show you the results. This is something that was enabled by using twisted boundary conditions. We were trying to calculate whether the electron gas would be ferromagnetic. And there's a long history of this going back to the early days of quantum mechanics. They were wondering whether electron gas could explain magnetism. The answer is no, it can't. But then it's just a theoretical question about whether electron gas could become ferromagnetic. And I won't go through. I'll just show you our results, which are really nice. This is the energy of the electron gas at these different densities. These are very low densities, much lower than any metal, RS of 40, 50, 60. And this is the polarization. So what we did was we would take a system of, say, 100 up electrons and 50 down electrons. That has a polarization of about a half, right? And we would calculate the energy using twisted boundary conditions. And this is a curve that we would generate. And you see that at RS of 40, the lowest energy state is one that has zero polarization, but there seems to be a second order transition to a partially polarized state as they get more and more strongly correlated. And here shows how we estimate where the transition should occur, about 50, RS of 52. And in fact, this is still in the liquid because we estimate that the Wigner crystal is at RS of 105 or so for the three-dimensional electron gas. So this was, as I said, and this is the first calculation we did with our twisted boundary conditions and also using our backflow wave functions, which should be quite accurate in this system, and using fixed phase, diffusion Monte Carlo, all the things that I talked about today. It's not tested. Unfortunately, you can't make a system like the electron gas at these densities because any material would have too many defects to be a pure electron gas. Those corrections would dominate. Okay, I'm finished with this. What I missed was the reptation and excited states, and maybe we could fit it in Thursday or Friday. Any questions? Yeah, Nick?
Trying to understand this twist average boundary condition.
Yes.
It's not used in density functional theory. Maybe you just need to direct me to the right paper, spend your read it in more detail.
I can't quite. Say that again. It's used in density functional theory?
No, it's not used in density functional theory.
Well, it actually is because density functional theory does a Brillouin zone integration of a unit cell. And this is the equivalent, instead of a unit cell, to a supercell.
Okay.
It's the same as doing a K-point integration.
I
which is, yeah. But I think the reason why it hadn't been done earlier in quantum Monte Carlo is that people didn't want to deal with these complex wave functions. But actually, it's not that bad to deal with them. And so I forgot to mention there's one difference with DFT. In QMC, the twisted boundary conditions do not have to slow down the calculation because the twist angle is another variable that you integrate over. And in Monte Carlo, it doesn't really matter how many variables you integrate over. One more variable is not that much worse. There could be effects, like you might have to do a DFT calculation at each twist angle, and that would slow you down. But the Monte Carlo part doesn't actually slow down because you have twist averaging. And we actually use that in our simulations of hydrogen, and that speeds things up. It actually gives you another variable to parallelize over. Yes?
Would it be the twist angle equivalent of using the special K points?
Well, that would be...
For solid state, if you just use a gamma point, or maybe if you have periodic boundary conditions in the supercell, you're getting a gamma point at two special points, and there's two pi symmetry. But if you shift off the gamma point, you have
well, there are certainly relations between these special K points that you use. But when you take something like electron gas, there wouldn't be any special K points, right? I mean, you have translational symmetry. And so what you're really trying to do is to map out very carefully the Fermi surface, right? Because it matters a lot whether how many states are inside the Fermi surface or not. So it's like when you're doing a DFT calculation of a metal, having to integrate very carefully around the Fermi surface. For an insulator, say you take silicon, you would want to choose your twist angles to be those special points that you use in DFT. For an insulator, it's a bit different because there you don't have a discontinuity in occupation number anywhere. Any more questions?
You mentioned that diffusion Monte Carlo is super variational.
Well, okay, all I meant was it looks, it's variational, you have an upper bound, but it looks for the best upper bound consistent with your nodes. So it's like you have infinite flexibility in between the nodes. That's all I meant. Maybe not the best word, but there was another question, yeah?
You said you simulate 3D electron gas in the box.
Yes.
But instead box, let's suppose the sphere.
No, it's not a sphere. It could be a cube, but it's periodic. It's like a torus, right? It's periodic box. But it's like a cube, or it could be a rectangle, or it could be a parallelepiped. But it has to be a space-filling shape. So that's why we wouldn't use a sphere. You might want to use something like a dodecahedron, or some other space-filling object. But it has to be generally speaking, we use a Bravais lattice for a supercell. But it's a lot easier if you use a rectangle to write the code. That's kind of at the inner loop, the periodic boundary condition. So
Instead, the plane wave, that's the different basis, like spherical SL function.
you're back to the sphere. Nobody would use a sphere. A sphere is not space filling. So if you want to use periodic boundary conditions, yeah.
How does the computational cost of the averaging process of the twist angle compare with periodic boundary condition?
Oh, okay. You mean how does, maybe rephrase it, how, when you do twist averaging, then you have to use complex wave functions instead of real wave functions. It turns out that modern processors can deal with complex numbers only a little bit slower than real numbers, maybe 20% or something. I think that used to be the number. I'm not sure why that's true. That has to do with hardware. That is, you're just approaching the peak performance of a processor closer by using more of the pipes and things like that. Of course, that's not mathematically true if you actually, because you have a lot more multiplications. So the part of the code that has to deal with the Slater determinant has to be complex. It's all in those linear algebra. First, it's all generating the wave functions, and that could be somewhat slower. And then you have certain matrix operations that you have to do, but those are all these BLAS operations which run really fast, and that usually doesn't dominate. Of course, the memory would be twice the memory. However, there's a big advantage in the code being simpler with complex wave functions. With real wave functions, you have a lot of finite-sized issues because the Bravais lattice doesn't necessarily, the number of particles may not, you may have a degeneracy at the Fermi surface to resolve, and you can resolve it different ways, and it becomes very complicated. But when you have twisted boundary conditions, you almost always have non-degenerate ground states, and they become much easier for your code to deal with, I would say. So that's in terms of human time, I guess, debugging time, but, But you might, there could be difference in time step errors and things, but I think in practice there's not really a big difference. Well, maybe we should cut this off.
Produced by OCE Atlas Digital Media at the University of Illinois, Urbana-Champaign.